Hello, everyone. I am Gloria Sanchez from Metropolitan Area of Barcelona, and welcome to this webinar, Breathe the Change, Innovation and Sustainability in Air Treatment at Waste Management Plants. This session is a part of a broader theme of the EU Green Week 2025, titled Circular Solution for a Competitive EU. The EU Green Week has been a flagship event since it launched in 2001. Bringing together policymakers, industry experts, and citizens from across Europe to promote and discuss the latest environmental policies and initiatives. Over the years, it has become a catalyst for environmental change, driving the transition toward a greener and more sustainable Europe. Topics today is particularly relevant in the context of the Green Deal and the push for circular economy practices. Waste management and air treatment are the forefront of these efforts, as they are essentials for minimizing environmental impact and ensures healthy, more sustainable communities. We are going to hear from exceptional speakers who will share these insights on innovative solutions in air treatment at waste management plants, showcasing real-world examples of how we can reduce emissions and foster sustainability. Our webinar today will run from 10 a.m. to 1 p.m. Spanish time. We will have a short coffee break in the middle to rest and recharge. We encourage you to ask questions in the chat at any time during the presentations. At the end of the webinar, we will have a dedicated question and answers session to address your question and foster discussion. Before we begin, we'd like to ask that in your profile, you indicate your full name and your organization. This helps us all connect and make the most of this networking opportunity. Thank you for joining us today. Your active participation is key to advancing this important conversation and making a real difference in our shared environment. So, without further ado, let's begin and explore how we can bring the change toward a more circular and competitive Europe. Thank you. Thank you, everyone. The first session, the title is LIFE ABATE Project Innovation for Cleaner Air in Waste Management Plants. This next presentation is sure to be mindful and engaging, and the first speaker is Raquel Lebrero. Raquel Lebrero is Associate Professor in the Department of Chemical Engineering and Environmental Technology at the University of Valladolid, Spain, and Senior Researcher at the Institute of Sustainable Processes. Her research specializes in biological waste gas treatment and valorization, odors, volatile organic compounds, greenhouse gases, syngas, with an emphasis on generation value-added products with a circular economy framework. Her expertise extends to biogas and wastewater treatment through microalgae technology and indoor air purification. She presents the LIFE ABATE solution. This is a European project. Good morning, Raquel.
Good morning. Thank you, Gloria. So I'm going to share my screen now. Let's see. Okay, I think it's okay now. You can see the presentation, right?
Yes, it's all right.
Okay, thank you. Okay, good morning, everyone. Thank you, Gloria, for the introduction, and thank all of you for being here today, for attending this webinar. I'm here today as the coordinator of the LIFE ABATE project, as Gloria mentioned, which is the one that we are going to explain now and in the two following sessions. So I will give you, in my presentation, the aim is to give you an overview of the project, of what are the technologies that we want to test and to validate. And then my colleagues, other partners within the consortium will explain you further about this project and the solution that we present. So the complete title of the LIFE ABATE project is, as you can see it here in the screen, is Marketable High-Performance Compact Technologies for the Abatement of Volatile Organic Compounds in European Union Waste Treatment Plants, Decreasing Carbon Dioxide Emissions and Energy Consumption. So the technology, the demo plant, will be first located in the Eco Park 3 in Barcelona, under the supervision of the metropolitan area of Barcelona. And then we will validate the technology in the last year in Las Dehesas in Madrid, as Arantxa will explain you later in the next presentation. This project started in October 2023, and it will run for 4 years. So we can say that we are still at the more or less beginning of the project. So we will start the demo plans next September, but we have some preliminary results we will present you today. As I said, we are University of Valladolid is the coordinating beneficiary, and we have another 5 partners. You can see here. Have IRIS Environmental Technologies. They will be responsible for the biological solution of the demo plant, which is, I will also explain you later, which is a 2-phase biotrickling filter. We have Metropolitan Area of Barcelona that will run the technology in the Eco Park 3. We have also Calfrisa. They are the company expert with expertise in the rotoconcentrator, in the concentration state, and they are also performing all the detailed engineering of the demo plant. We have the Polytechnic University of Catalunya. They will be in charge of the greenhouse and also the life cycle analysis of the project. And finally, we have SCC that are in charge or responsible for the demonstration of the plant in Las Dehesas. So just for you to have an overview of our consortium. But what was the main problematic or the main challenge that triggered the development of this project? Well, what we know is that nearly 700 waste treatment plants, or more specifically mechanical biological treatment plants that we have right now across Europe, are releasing over 4 million tons of volatile organic compounds annually. And these emissions, these gaseous emissions, are very tricky for treatment because they have very special or distinctive characteristics. They are characterized by really high airflow rates and trace level concentrations of a broad spectrum of VOC families. So basically, we have huge volumes of air streams with a huge number of volatile organic compounds with different characteristics and at very low concentrations. So the treatment of these emissions is always has been always very challenging. Right now, current technologies that are using MBT plants for the elimination, for the removal of these VOCs, are either physicochemical, such as, for example, thermal oxidizers, or they can be also biological, such as biofilters. But these technologies, these solutions are usually high costly, they consume a lot of energy, and they have also a high carbon dioxide footprint. And if we look at the biological technologies, at the biofilters, they usually are challenged because they require a lot of space. They have a high footprint. So the objectives of this project, of the LIFE ABATE project, were to develop technology that could reduce volatile organic compounds and other emissions with reduced energy requirements in terms of natural gas and of electricity, and also therefore reduce the exploitation costs of MBT plants, while of course complying with current legislation. And at the same time, we aim at valorize the carbon dioxide that is produced in greenhouse farming. So we avoid the discharge of this carbon dioxide to the atmosphere. So in the project, we propose two technical solutions. The first one is a combination of a pre-concentration step, regenerative thermal oxidation, a physical removal of the compounds, and then the greenhouse. And in the second solution, we are proposing a rotoconcentration step, a pre-concentration step, followed by a biological solution, a two-phase biotrickling filter, and then the greenhouse. I will explain you both technical solutions or both ideas more in detail now. So the project aims to transform this waste treatment sector for a cleaner, more sustainable future, as I said. And what we have is we have the mechanical biological waste treatment plant. We will extract our waste emission, more specifically 20,000 cubic meters per hour. That contains a low VOCs concentration. And here we have the first step, or the core step of our solution, of our project, which is a zeolite rotoconcentrator. This solution has been tested in other industries, but it has never been tested for this application. So this is a huge, an important innovation that we want to test. After this pre-concentration step, what we are going to do is we will obtain a concentrated stream with smaller air volumes or airflows and higher VOCs concentration. And they will be treated either in a regenerative thermal oxidizer. This is the technology that right now is running in Eco Park 3 for the treatment of the VOCs, or using a two-phase biotrickling filter, which is a biological technology that is a modification or an innovation over a conventional biotrickling filter. What we are doing here is we are adding a second organic phase, a silicon oil, so that we improve the mass transfer of the volatile organic compounds to the microbial community. So we have these two lines, these two solutions that we will test. And finally, what we will obtain is a airstream that is clean of VOCs, but it has high concentrations of carbon dioxide. So we will direct it to a greenhouse to see if we can use this carbon dioxide to improve the growth of agricultural crops. Here you have a clear schematic and very simplified vision of those two technologies, of these two solutions. Again, we have here the MBT plant, the VOC diluted stream. It will go through a rotoconcentrator where we will obtain a VOC-free air, 18 cubic meters per hour. We are concentrating 10 times the inlet air stream, the inlet contaminated stream. So we will have only 2,000 cubic meters per hour to be treated now, but with 10 times higher VOC concentration. We will see what is the reduction in energy consumption in the costs of the RTO, of the regenerative thermal oxidizer. And we also test, as I said, this two-phase biotrickling filter as an alternative, more sustainable solution to conventional physicochemical technologies. And finally, we have this greenhouse that will use the carbon dioxide for crops growth. So this is the main idea of the project. As I said, we have finalized all the detail engineering. We are finalizing also the construction of the demo plant that will be started in September in Eco Park 3. But I want to show you also some preliminary results that I think they are very interesting that were used as the baseline for the design of this of the technology of this demo plant. We performed some sampling campaigns for the identification and quantification of volatile organic compounds in the Eco Park 3, in this MBT treatment plant. These two sampling campaigns use different sampling methods and analytical methods, but and I just want to focus on the main results. As you can see here from the first campaign, what we saw is that isobutane, butane, and ethanol were the main VOCs contributing to the concentration in the indoor air of Eco Park 3. And the ones that contributed most to the odor were D-limonene and ethanol. And in the second sampling campaign that we use a more complex support for sampling and analytical TDs GCMS for the identification and quantification, we could identify 115 compounds. So just to take into account that we are targeting the removal of most of them in our solution. The ones that had the highest concentration were ethanol and limonene. And here you have the ones that contributed the most to odor, which were acetaldehyde, ethyl butyrate, and butanoic acid. So of course, this poses a big challenge for the technology, for the project, because as I said, we detected a lot of different compounds from many different families, and we had to prioritize. So our prioritization was based on first on removing those VOCs with greatest health risk, those that were most abundant in our samplings, those compounds whose concentration exceeded the odor threshold, and then we had to also prioritize different compounds over others. And this selection of these results were the ones that guided the selection of the zeolite matrix for the rotoconcentrator. And also, we use these results for the preparation of the inoculum of the two-phase biotrickling filter. We also started, as I said, to enrich and to produce this inoculum for the biological technology for the two-phase biotrickling filter. As you can see here, this was our first reactor. We are now increasing the volume of this inoculum. And basically, you can see here that we selected some of the most important or abundant compounds. We were able to remove biologically acetaldehyde, ethanol, butanol, ethyl acetate, and terpene. And the terpenes, these were the ones that we were feeding to the system, and they were all very well removed. But the limonene or alpha-pinene had not very stable and low removals. So what we did was to add this organic phase to the system, this silicon oil. So we converted the system in this biphasic biotrickling filter. And as you can see here, we were able to increase a lot the removal efficiency. And for about 200 days, the system was operating with removal efficiencies over 90% in the biotrickling filter of all the compounds. So we had very good results at the laboratory scale, and these ones we're expecting to translate them into this demo scale.
One minute, Raquel.
Okay. Just these were some pictures of the microbial of the microorganisms, just for you to see that they were not only growing on the aqueous phase but also on the interface and the silicon oil. Well, here you have the expected impacts. These were the some numbers that we did at the beginning of the project, but we have our partner from Polytechnic University of Catalonia that will present these impacts later on. So you will hear more about the energy savings, reduction of greenhouse gases, VOCs, OPEX, and natural gas savings. So this will be further treated later. And just to end the presentation, our project is clearly aligned with the goals of the European Green Deal 2030 Climate and Energy Framework, the European Union's carbon neutrality, and other European Union directives for minimizing volatile organic compounds emissions and other events from MBT plants. And also we are expecting to include this our technology as the best available technologies in the BREF document for waste treatment, and hopefully to consider it in the development of European Union policies. So this is all from my side. Thank you so much for attending the presentation, and I hope you enjoy this webinar. And I invite you to see or to check our website, and also to follow us on the different social networks to see the next steps and of our project.
Thank you,
Thank you so much.
Raquel. I would like to remind the audience that you can put your questions in the chat. Thank you. Let's welcome our next speaker, is Aranzazu Alonso. Is indeed an accomplished professional in the field of waste management and treatment. With over 20 years of experience, she has made significant contributions to FCC Medio Ambiente, particularly at Las Dehesas biomethanization plant. Her career began with her education as an agriculture engineer from the Polytechnic University of Madrid. Over the years, she has played a crucial role in the development of the operation of Las Dehesas biomethanization plant, which is a key facility for managing organic waste in Madrid. Currently, she holds the position of head of treatment at FCC Medio Ambiente in Madrid, where she continues to lead and innovate in waste management practices. Okay.
Thank you very much, Gloria, for the introduction.
You're welcome, Arantxa.
And I'd like to come back to. Can you see it? The presentation?
No.
No. Okay. Come back.
Now, yes.
Yes. Okay. Then, FCC is Medio Ambiente is one of the members of consortium of Abate project, and I'd like to thank the opportunity to participate in this webinar. And I'm going to speak about the replication of the LIFE ABATE solution at Las Dehesas biomethanization plant. The definition of deodorization is the process of removing or neutralizing unpleasant odors from a substance, space, or product generated during the management and digestion of organic waste. But we know it involves more than simply eliminating bad odors. When we eliminate the particles and gases responsible of odor, such hydrogen sulfide, ammonia, and VOCs, we improve air quality inside and outside the plants, reducing unpleasant odors that can cause discomfort to workers and nearby populations. That contributes to a safer, healthier, and more socially acceptable working environment. It also contributes to environmental protection. When we capture and treat VOCs and these unpleasant smelling gases, we prevent their release into the atmosphere and thereby reduce air pollution. And furthermore, it is a way of complying with regulation regarding limit values at the plant's emission source. These are limited to 5 milligram cubic normal meter for particles, 40 milligram for cubic normal meter for VOCs, and 1,000 unit odor for cubic normal meter for odor concentration. According to this Commission implementing decision from European Union, with established conclusions on best available techniques for waste treatment. In the biomethanization plant of Las Dehesas, deodorization plays an very important role. The process begins. Okay. In this. Okay. The process begins with the reception of waste. We receive the organic fraction of selective collected municipal solid waste from the city of Madrid. This is the brown bin. The waste undergoes pre-treatment to achieve the condition required for the anaerobic digestion process. And the biomethanization takes place in 5 digesters. The process is anaerobic, dry, and mesophilic digestion, with a residence time of about 21 days. The products obtained in this process are biogas with a 55% methane concentrate that is sent to an upgrading plant and transformed into biomethane, and digestate that is dehydrated and then sent to the Cantiles composting plant to produce compost. Finally, the plant has 2 auxiliary facilities. A leachate treatment plant, where the liquid fraction of the digestate is treated, an advanced biofiltration system, where the air from the most problematic areas of the plant, pretreatment, methanization, and the digestate storage, is treated. The biofilter is an advanced biofiltration system and was built in 2021. This was a City Council of Madrid project in order to improve the deodorization system of Valdemingome facilities. A biofilter is a building made of concrete with 3 floors or section identical in surface area and treatment capacity. This total surface area is about 1,300 square meters with a capacity to treat up to 160,000 cubic meters per hour of air. The stream of air is extracted from the most problematic areas of the plant, and first is humidified in a scrubber to ensure that the air arrives in optimal humidity conditions and free of dust or particles that could inhibit the biological reaction inside the biofilter. The scrubber is a tank filled with a plastic material where the polluted air is countercurrently washed with water. We use the water, this water is the permeate reuse from the reverse osmosis in the leachate treatment plant. And once pre-humidified, this air is injected into the biofilter and distributed in the 3 sections. The biomedia is an inorganic clay covered with a specific microorganism that oxidize the gases present in this polluted air, transforming them into CO2. This biomedia is the key for this advanced and innovative deodorization technology. And this is the biofilter that we use now in plant. But we are participating in this ABATE project, this innovative ABATE project, and in the plant, IMAS DESAS is the name of our research and development center located in the plant. The objective of this center is to promote research and development projects like ABATE, and we install prototype to value-added processes, services, and products. Several projects are currently underway. One of these is a LIFE ABATE project, which aims is to reduce VOC and other emissions, and also reduce the operating cost of the deodorization system, as Raquel has explained very, very well. And in addition, it will transfer this CO2 produced to a greenhouse for agriculture use. The ABATE solution to be installed at a biomethanization plant in Las Dehesas will treat a flow rate of 20,000 cubic meters, normal meters per hour at 35 degrees, loaded with VOCs. First, the stream will be passed through a particle filter. Next, the stream loaded with VOCs is heated and concentrated. The outlet stream will be at 52 degrees and 10 times more concentrated, so that the flow rate to be treated will be 10 times lower. This stream will be treated in a two phases biofilter percolator through biological degradation. Finally, a percentage of this treated air free of VOCs will be sent to a greenhouse for use in agriculture, vegetable and ornamental plant cultivation, to use this CO2 for the growing of these agricultural crops. The rotary concentrator is the first equipment with a great importance in this process, and is where the concentration of VOC stream will take place. The most important advantage of concentrating this stream before cleaning are reduction in the volume of air to be treated, decreasing the size of this equipment, and therefore the investment cost and energy consumption of the treatment is also reduced. Also, the system is more compact and saves space. The equipment is easier for installation in the plant and dismantling if it was necessary to move to another place. And greater system efficiency is expected. As concentrating the VOC stream, we allow the system to operate closer to its optimal load range. And this will increase the removal efficiency, we hope. The concentrated air will be treated in the biotrickling. That is a biological VOC treatment system. Here, the polluted air passes through a bed of inorganic material irrigated with a solution rich in nutrients and microorganisms. When the airstream passes through the bed, the pollutants dissolve in the liquid recirculated inside it. The microorganisms present in the biomedia oxidize the contaminants into non-toxic compounds such as CO2. Biofilter has some operational advantage. Unlike biotrickling, it does not require liquid recirculation. It's easier to operate and does not require liquid effluent management or purging. But a ABATE solution has several strengths worth highlighting. Operating parameters, pH, nutrients, and contaminants, and temperature are better controlled in biotrickling, we hope. Biotrickling supports higher loads of contaminants, such as VOC and acid gases. Biotrickling is more stable. It does not dry out or clog easily. And biotrickling performs very well when load has high variability, is variable. After biotrickling, the airstream rich on CO2 will be used in this greenhouse agriculture, and this also reduces the concentration of greenhouse gases emission to the atmosphere. Current operation in our biofilter
Arantxa, un minute, sorry,
Okay,
minute,
okay,
one
okay.
minute.
1 minute. Plant are we have an efficiency of between 19 and 19.5 for the removal of VOCs. An intermediate energy consumption and carbon footprint, low operating cost, but some difficulty in controlling these operating parameters as humidity or pH. What we expected in ABATE solution is a similar VOC removal efficiency, 92, a reduction, an important reduction in energy consumption and carbon footprints, lower operating costs, and resolve some this operation problem that we have now in the biofilter. The preliminary LCA analysis suggests a high possibility of an increase in energy consumption due to the rotary concentrator. Although it considers the reduction in the footprint in square meters and consider an annual saving of around 87 in operating costs. Compared to the current equipment, it's a very significant difference, and a compact system requires less maintenance. Then now it is necessary to validate this technology and obtain these experimental results when the prototype is put into operation in Madrid. The design of the equipment and the preliminary LCA analysis suggests that the ABATE solution at Las Dehesas biomethanization plant could be viable and competitive for replication in other mechanical and biological treatment plants for municipal solid waste. And in summary, the solution proposed by ABATE offers the big advantage for deodorization. One is the reduces space occupation and lower footprint. 2, long lifespan of the packing material of the 2PVTF compared to a conventional biofilter. Significant energy savings, minimal operation costs, totally automated system, a good adaptation of the 2PVTF biomass to the fluctuation in polluted gas concentration, and environmental friendly technology. Then thank you very much for your attention, and I'm sure this project will be a great project, and we obtain good results of this prototype. Thank you very much.
Thank you, Arantxa. Now we continue inside the LIFE ABATE consortium, now with Marcel Macarulla. He is Associate Professor at the Polytechnic University of Catalonia, belonging to the Construction Research and Innovation Group named GRIC, expert in the integration of greenhouses with buildings of various typologies to investigate environmental assessment and circularity synergies, with a focus on energy optimization, indoor air comfort, and AAK modeling. Head of RG Lab, a living lab that integrates a greenhouse into a building's ventilation system to explore real case indoor air modeling and energy efficiency.
Okay. Thank you, Gloria, for your introduction. I'm sorry for this small issue. As Gloria mentioned, I am Marcel Macarulla, and my presentation is Expected Impact LIFE ABATE Reductions of Emissions, Energy Efficiency, and Cost Savings. And this is the content of my presentation. I will explain you the current configurations. I will not go in deep because my colleagues explain it very well. I will just explain the flux of energy, water, and emissions. Then I will explain you the same for the proposed configurations. I will explain you how we did the LCA modeling and the preliminary results in terms of LCA energy costs and energy efficiency. Okay, and finally I will present you the preliminary conclusions and when we plan to obtain the final results. Okay, the first configuration is in the eco park. We have a regenerative thermal oxidation. Okay, that is treating all the air that is inside the eco park, and how is it working is through the use of natural gas and electricity to move the air. What we are doing is to burn the pollutants and then avoid these others. Okay. This is the last DSS biofilter that my colleague just explained it. I will not explain it again. And here what we are using is natural gas, electric input, water input, and fungicides. Okay, and then the electricity input. Then, which are the solutions that we propose? The idea here is to take the air from our installations, put it in a roto concentration, just to treat less air than we are doing right now, and then treat with a regenerative thermal oxidation. Okay, and then put it in the greenhouse. Here, the idea is that the regenerative thermal oxidation is using or is sending the concentration is using recovering waste heat from the RTO, and the greenhouse is recovering the waste heat and also the CO2 of the whole system. Okay. And then here is our system, is a pilot plan. Okay, the idea is we will treat 20,000, 2,000 will go through the RTO and then to the greenhouse, and then we have 80,000 that is going to the exterior. This is a pilot plan. Then to avoid others, we will put again this just to be sure that the roto concentration is gathering or is catching all the others. We are putting these air inside our installations just to be sure that the others are completely removed. In the case of the biofilter, this is the scenario. Okay, the idea is the same. With the roto concentration, we treat less air, and then with electricity, water, and silicone oil, what we are doing is to treat the air and then put it inside the greenhouse. Here, the idea is to recover the waste heat in winter and to recover the CO2. And again, what we are doing here is to be sure that we are not putting volatile components in the air. We are reusing we are putting the air that it's going outside the roto concentration inside the facility again to be sure that we are not throwing others to the external part of the building. Then the LCA modeling, these are the configurations that we analyzed, the ecopark plus the RTO, the last days with the biofilter, and then the roto concentration, the RTO, and the greenhouse, and the roto concentration with the two-phase biotrickling and the greenhouse. Here, what you have to notice is that in the ecopark, we didn't put the greenhouse, and in Las Dehesas, we didn't put the greenhouse, and as you will see, the results are a little bit strange, but the point is that here is a pilot, and probably here we should plan which is a typical greenhouse that we can reuse. Okay, then I will explain you how we did this extrapolation. We focused on the operational phase of the technologies, okay, mainly on the energy consumption and the rest of the things. And we considered a continuous operation between 24 hours a day and an expected lifetime of 25 years. And we declared the functional unit is 1 meter normalized meter cubic per hour of treated gas. But you will see in my last slide that this is a little bit tricky because at the end we have two functional units. We are treating the air, but at the same time we are producing food or crops, and this is something that we have to analyze in the future. But right now, without knowing which is the crop we have to use and if this crop can be consumed or not, the analysis changes. Okay. Then the LCA, we used the software Sima Pro, the database EcoInvent, and this method, and the indicators that we used are these ones. Okay, climate change, ozone depletion, ionizing radiation, photochemical ozone formation, particulate matter, human toxicity for non-cancer and cancer, acidification, eutrophication, fresh water, eutrophication marine, eutrophication terrestrial module, eutrophication terrestrial, ecotoxicity, fresh water, land use, water use, resource use fossils, and resource use minerals and metals. Okay. These are the results with reference to the ecopark. As you will see, the best solution here is the Las Dehesas. However, we are not considering, as I mentioned before, the greenhouse. Okay, if we put the greenhouse, we will see an improvement. However, here we are comparing only the two systems, like the two options, like we propose. We have a problem of scalability because we don't know exactly which are the costs of our system if they work on in a bigger system. Right now the calculus are done, the RTO, the ecopark, and Las Dehesas with real data, and these two are done with the pilot plan. Then this is not helping us to obtain good results. As you see, the pilot plan has no discussion, better impact than ecopark 3. However, in Las Dehesas, here the problem of scale is penalizing us, and for this reason we have this increase. But we expect, as my colleagues explained before, that when we can normalize the values or obtain better estimations of which are the calculus that the real data that we consume here, we can reduce the climate change impact and the rest of the impacts. Okay. Then, if we talk about energy efficiency, you see here that these are the kilowatts hour per normalized meter cubic. Okay, and these are for the old configurations. However, to compare, we need to add a greenhouse to the baseline scenarios, and we considered that in the Mediterranean area, if you want to hit a greenhouse, okay, you need at least 381 kilowatts hour per square meter per year. Okay, then if we want to do an estimation of the energy savings of the whole system, okay, we have to consider the ecopark with the greenhouse, Las Dehesas with the greenhouse, and then our systems with the greenhouse. If you see here, we are recovering waste into the waste generated, the waste heat generated in ecopark and Las Dehesas, and this helps us to avoid the energy consumption on this potential greenhouse that is a 7,000 greenhouse. Okay, for a treated this volume of air treated. Okay, if you see here, the reduction in terms of energy is very high. If we talk about the cost savings, here it's a matter of which is the energy that you use. If you use more electricity, the costs are higher than if you are using gas. I took these two costs from the last report from Red Eléctrica, that they say that in Spain the average cost of an industry is 0.10 euros per kilowatt, and the gas is 0.04 euros per kilowatt. Okay, but of course this cost should be taken carefully because it depends on market situation. Okay, and here the actions that we are doing also is recovering the waste heat in the greenhouse. Okay. Then, if we talk about the preliminary conclusions, first of all, we have to say that the estimations are still preliminary, and the results can vary along the project. You have to know or to consider that the estimations of Las Dehesas and ecopark was very easy to do because we have all the information from our colleagues. All of them provided us all operational data that we need, and then this data is there is no discussion. However, for the operational phase for our pilot plan, we have small equipment and we have the problem of scalability, and this is penalizing our estimations, but we have to find a way to compensate that. Regarding at this stage, we only considered the operational phase because we don't know which is the impact of building a new regenerative thermal oxidation plant or a new biofilter. Okay, but this is something that we have to do in the next steps of the project. Here we see that the Las Dehesas is the one that has low impacts in all categories, but here the problem is which are the viable crops that you can grow, because if you can grow crops, then you have 2 functional units, and then the results will be much better. Okay. Then Abate solutions ensure a reduction of all impacts in all categories, especially in climate change. And again, and this is something that I want to explain and to remark, is that the reductions are expected to be even more significant once the project is scaled up, and when we know if we can reuse the crops or that we have inside, if we can eat the crops that are inside the greenhouse or not. Another thing that is important of the Abate solutions is that they need less space. They are more space efficient, and we have a low capex. Okay, and then another interesting thing of this system of the system proposed is that it's viable to inject CO2 in greenhouse. Right now, here in Spain, it's not usual to inject CO2. We know that in other countries like Holland, for example, they are injecting CO2 in technified greenhouses, but in Spain is not a common practice. Then if we can reuse this CO2, or we can put this CO2, then we can reuse the food and plants that we grow inside the greenhouse. Then we will have to deal with these 2 functional units, the treated air and the food plants and production. Okay, the food plant production. Then I think that here is the most interesting thing is when we will have final results. With the project started on the 16th of October on 2023. Right now we have the baseline indicator establishing a continuous monitoring ongoing. Okay, and the idea of the initial plan was in month 46, that this means more or less in October 2027, or this is the end of the project, but in September or August, have the LCA and the LCC completed. However, we had some problems during the implementation, and probably we asked for an extension of the project. Then this date will be modified. And Gloria, I tried to be quick just to recover the time that I lost during my connection, but I think that I achieved the objective. And thank you very much. And here you have my contact details, and if you have doubts, you can put it on the chat, or I think, Gloria, we have at the end of the session open questions, right?
Thank you, Marcel, for keeping the timing, although the incident. Moving on, we'll now hear about the session 2, the keys to innovation in the management of volatile organic compounds and others. We are honored to have here Carlos Nietzsche Díaz, is the director of Ambiente Todora in Bilbao, Spain, a company focused on environmental consultancy with a special focus on odor management. He has over 20 years of experience in odor management. He holds a BS degree in chemistry from the University of Seville in Spain. He has been responsible for projects related to odor management in many countries around the world. He is the main editor of the olores.org website and has been a keynote speaker at several international conferences. Carlos served as the president of the International Environmental Society of Odor Managers, and he is a member of several communities dealing with odor management in International Water Association, World Economic Forum, Amigo, UNE, and CIEN. He is with us to talk about technological solutions in the treatment of odors.
So thank you very much, Gloria, and the whole team for this introduction and for inviting me to this talk. That is going to be fast. I promise it's going to be fast. And I put the clock so that I don't go longer than my time. All right, so today I'm talking about odor control. And because I have just 15 minutes and odor control is just a really large science, I'll go just through some pictures and try to describe you a little bit about which is the stage of the odor control of the state of the science. All right, so who are we? We are Ambiente Todora. We are based here in the north of Spain. Ambiente Todora means, not many people know, that means everything related to odors in Latin language. And we are based in Bilbao. But we do projects worldwide. And this is the team. Last Thursday, we had we went for a trail, and we had a fantastic time there. If you want to know a little bit about odor control, there is a directory in this website, dolores.org. This is one of our websites, and there you will see all physical, chemical, biological odor control abatement methods. And there, if you need something, it will be there. All right, so this is the typical approach. I've done this talk a few times, but I think this is the best way to approach odor control methods. And so you have the liquid phase and the gas phase treatment. And in the liquid phase, you can go through a chemical, biological, and a physical treatment. So if you go to a chemical treatment, this is mainly used for wastewater. So you have air and oxygen injection. You can inject air in the water. This air has two effects. First, oxidize some sulfur compounds, and the second effect is that it gives oxygen to the bacteria around, so that instead of consuming sulfate, they will consume oxygen. So it's a good abatement method. And then oxygen, you can also use oxygen. It's 5 times more soluble than air, so it's another option. Then you have chemical oxidations. For example, using chlorine compounds, you oxidize those volatile organic compounds, or hydrogen peroxide, potassium permanganate, ozone, which is typical. You see here the ozone. I try to include the sources when I get the pictures. And nitrates, this one I didn't include the source. Iron salts, this is from Webster. Most of them are good friends. I know most of them. And the pH adjustment. Depending on the pH in a liquid, you may have a higher or lower emission of hydrogen sulfide, which is one of the typical indicators, not the only one. Then in liquid phase treatments, you have the biological treatment, and there are 2 approaches. There are 3. The first one is the recirculation of activated sludge. So you are in a wastewater treatment plant, and then you can recirculate the activated sludge and put it at the head of the system, at the beginning of the system. And because there are nitrified effluents, remember we use nitrates there. Those ones will help to improve your odor emission in your plant, in your wastewater treatment plant, in case you have it. And another approach is the oxidized ammonium recirculation, in which you get oxidized ammonium from, for example, from a centrate nitrification, or from the nitrification part, and then you introduce it in the inlet. So this is a very cheap way to reduce your odor emission if you have a wastewater treatment plant with problems of odor complaints. And it's not here, but sometimes some people use enzymes for biological treatment. I didn't include it here because publications I have found around, they are not that positive. And then you have a physical treatment. for water, remember, and you have this technology, which is a vertical seaward drop. It's a vortex flow, so you use it in a drop when you have a drop, and the water goes like this, so you get aerated the water, and you decrease the turbulence, which emits auras there. You can use stripping, which is a typical way of dealing for. This is done when you have high concentrations of volatile organic compounds in your water, and you can strip it. This is another way to do it. And then for gas phase treatment, in a chemical treatment, you have the typical scrubbers, gas scrubbers. This is a series of 4 scrubbers. And a scrubber is just a shower with liquid that can be water, or it can be other compounds, oxidizing compounds, or different types of compounds to wash, to scrub the volatile organic compounds from the airstream. So you get the air is coming through here. You wash this air, and then the air goes out cleaner. Then for biological treatment, we have heard some technology here before, so I will not go longer here. So we have the biofilters, open and closed. But we normally prefer closed. Biotrickling filters, it has been explained before, and bioscrubbers, which are other technologies. And these biological treatments, they look the same, but they are for, you see here, for pump stations or underground places where you have wastewater collectors, and you need small technologies, and they could be biotechnologies as well. So you have here this one from BioRem. This is a pumping station in Canada, and there was no aura after that. A biotrickling filter, and this one is also here. You see this. This is the top of a wastewater collector, and then you put here, and they sell this. And for physical treatment, the typical ones are the dry absorption systems, and here you have different types of dry absorption systems. This one, for example, is for biomethane. It's made of, these are the typical activated carbon. This is activated carbon impregnated with permanganate potassium, and this is I think zeolite. And another one, I don't remember. And this is iron salts. They are made for biogas systems. So here you have one typical dry absorption system with activated carbon. Another physical treatment is the thermal oxidation, and we have heard about that before. So you have direct oxidation, which is just your flame directly oxidize the volatile organic compounds, which at temperature over 700 degrees, they get oxidized to CO2 and water. Then you have the recuperative. This is a recuperative in which there is a heat exchange that you can get this heat, and you can produce water steam if you want. Then you have the regenerative, which is this one, in which you use the heat from one chamber to heat up the other chamber, and for that you use a filling with the ceramic tiles. And then you have the catalytic, in which you use a catalyzer to oxidize those volatile organic compounds, but at lower temperatures. This is the good thing of the catalytic oxidizers. So you spend less money in using these ones, but they are more expensive than the other two. And flares. And I will speak a little bit about rotoconcentrators. There have been some talks about this, but I had to talk because I'm talking about auto control. And rotoconcentrators are much used for when you have industries with a high concentration of volatile organic compounds, like paint or refineries or things like this, which you have a very high concentration of volatile organic compounds, and it's just a disk in which the VOCs gets absorbed with the zeolite, and this disk is spinning. And when they get absorbed, they get to this section in which they are heat up with a heater, and those compounds are dissolved. Once those are dissolved, the zeolite is clean again, and then it goes to a cooling phase, which it gets cooled, and again it starts the system again. So I included this from this one of the partners of this this picture from one of the partners of this consortium. Then you have ozone that you can use. You could use in the water phase, but you can also use ozone in the gas phase, which is typical. Cold plasma technologies. I didn't have the time to put a picture here, but it's very much used. With cold plasma, it's just the electricity that goes through here, and this electricity ionize the gases and oxidize them. And photocatalytic oxidation, which is this one, in which you use ultraviolet and sometimes a catalyzer like titanium dioxide, and you are able to, with very low energy consumption, so they work very well. You get your good abatement efficiency rate. And this is another one. This is in Colombia. We were there a couple of months ago. All right, so which method should we use? So this is this typical graph in which we normally say, listen, this is from sorry, I forgot to put the reference. I'll include it for the next time, or ask me if you want to know the reference. It's very old publication. But anyway, we didn't like this because it didn't talk about Aura. So we went and we did our own table. You see here biofiltering, biotrickling with minimum and maximum flows, concentration minimum and maximum, efficiencies minimum and maximum. And from where did we get those data? We got those data from Vito. It's not here the reference. From Vito, I see Ilse is around. We got different data related to flow and concentration and efficiency rates. And we produced this graph, which is different than the other one. The other one looks nicer, but for us, it is like using those data from Vito. For us, it's more related to Aura. So, and these are some technologies, not all of them that I mentioned before. And here you have the efficiency rates, maximum efficiency rates. Oh. The Vito logo was here. Anyway, there is other types of technologies to abate odor. First one is elevated chimneys, for example, and you disperse the odor. And this one, this is a tall chimney, and this is a way to increase your plume. Then you can use covers, and there are different covers, rigid, floating, different types of covers. For solids, there are different ways of covering as well. You have this for trucks, lorries, this for composting plants, this one's for landfills. And then you have masking agents, neutralizers, odor encapsulators, and etc. They explain very well how they work. They generally have lower Kpix, but they will not give numbers on Aura abatement efficiency. But you just say that they work. So do they work? Maybe they do, maybe they don't, who knows? But there are other strategies like using meteorological data to control your Aura emission, using diagnostic odor dissipation models, prognostic odor dissipation models, use of instrumental odor monitoring systems, and many other. For example, using an odor management plan. But the best odor control strategy for any plant is working on process. If you want to know more, in Europe there are around 30 best reference documents related to different types of industries. And for example, in the farming or in the chemical industry or in the waste, you have the word odor mentioned a few times with some mentions to odor abatement methods. And thank you very much for your attention. If you have any doubt, I'll be waiting for your questions at the end of the session. Thank you very much.
Thank you, Carlos.
And my time.
Yes, 1 minute before. Nobody put questions in the chat. I encourage you to put some questions in the chat and we discuss at the end of the webinar. It's a real pleasure to introduce to the next speaker, Marc Binot, with a background in biological and industrial processes, is in charge of biological processes at Urbaser SA and has 25 years experience in the waste management sector. He began his career at Valorga in the field of anaerobic digestion. He has worked in Belgium, France, and finally Spain at Urbaser for the last 19 years. Over the last 15 years, he has worked mainly on all aspects of air treatment, anaerobic digestion, and composting. He has been involved in the design, engineering, and commissioning of large installations built in France and in Spain. Okay.
Okay.
Marc?
Hello.
Hello.
Yeah, you hear me? Okay,
Yes.
great. It's working. Okay. Thanks, Gloria, for the introduction. Thanks for the organization of the webinar, for inviting us to present. And I will try to make up some time. It's not so easy. The title of my presentation is Environmental Challenges of MBT Plants, VOCs, Unpleasant Odors, and Energy Consumption. I'm going to talk about the challenges we face in terms of odors in the municipal waste treatment facilities, the VOCs and the different type of concentration of VOCs we got in the different areas of the facility. And I will speak about how to reduce the operating cost of ventilation systems in industrial facilities, in our facilities. Okay.
Marc, if you are moving your slides, we don't see them.
No, not yet. Now. Okay.
Yes, okay.
Okay. So, unpleasant odor, when you start talking about municipal waste treatment plants, the word smells immediately comes to people's minds. I remember a few years ago, 10 years ago, I arranged a visit from a facility for my children's class, and 10 years later, all the teachers and accompanying adults are limited. Their memories are limited to smell. So this for the population. This is the main issue or thought they got about municipal waste treatment plants is the smell, the odors. Okay, so odors is a sensation, as you all know, the stimulation of sensory cells due to gas phase chemical compounds usually found in very small quantity below the threshold of analytical detection, but produce a response to our olfactory bulb, and we got this sensation of odors. The main odorant compounds, if we want to classify by the main groups, we got the sulfur compounds, H2S, mercaptans, thiol, sulfide, and polysulfide. So the azocomposites, ammonia and amines, aldehydes, ketones, organic acids, terpenes, alcohol, aromatics, aliphatic, and this is the main. There is more, but this is the main ones we got in when we speak about odor compounds. In waste treatment facilities, the main odor sources are the nitrogen compounds that originating from the decomposition of nitrogen compounds present in the waste. the compounds we get is ammonia, the urine smell, amines, fishy smell, the sulfur compounds from the anaerobic decomposition of the organic fraction. We got hydrogen sulfides, this rotten oak smell, methyl mercaptans, rotten onion smell, dimethyl sulfide, this cabbage smell, and dimethyl disulfide. This is also cabbage smell, mainly. Not working. Yes, no. We got also nitrogenous organic compounds originating during the decomposition of proteins and amino acids we got in the organic residues or in the food waste, and the VOCs. For example, in aerobic and anaerobic decomposition process of organic material, we have a very high production of VOCs. Yeah? That contain carbon and are volatile at room temperature. So we got the alcohol, aldehyde, ketones, esters, the terpenes, and volatile fatty acids. So here we got a table of some chemicals with the odor threshold in ppm and the characteristics odor sensation we got with all these chemicals. Okay. Now, if we focus on municipal waste treatment plant, we have some areas where we have a higher generation of odors. Okay, the first building or unit where we get this generation of odors is the reception and storage pit. Because when we get waste, especially waste with high content of biodegradable material, it's prone to decomposition and odor generation. The pit can be around 2 to 3 day capacity of storage. So we get the material in this pit during a lot of time. And depending on the country, the frequency of collection of the waste in the house is quite different. For example, for bio-waste in Essex, it's nearly 1 a week. So when the waste is coming to the facility, it has spent 1 week in a container. So depending on these two things, we can have a very high emission of VOCs and other compounds. Afterwards, we get the pretreatment and the initial sorting of waste, the shredding and circulation of waste through the facility to segregate materials, also release gases and particles that generate odors. After we have all the package of the biological treatment, okay, to process composting and anaerobic digestion of the organic fraction of the waste. So this is generate volatile organic compounds and also other odoriferous compounds. So we got here's the main units where we got this generation of other compounds. And if we focus on VOCs, there is a very close relationship between odors and VOCs. We all know this. These are diverse VOCs are a diverse mixture of chemicals that can range in odor from sweet to rancid. And these compounds are released during the decomposition of organic material, as I said before. And in waste treatment facilities, the VOCs are released by the anaerobic decomposition of organic waste without oxygen, anaerobic digestion, such as landfill and fermentation in digesters and putrefaction processes, the evaporation of solvent and chemicals in industrial or domestic waste, thermal processes, when we get inefficient incineration, you can have a very high concentration of VOCs at the output, and the composting processes, especially if it's not well controlled, there is lack of oxygen, excess of moisture, etc. And even if you are controlling quite well in a composting process, there is always, in a composting tunnel, there is always some area, some zone of the tunnels or of a reactor with with a lack of oxygen. So with, let's say, some points of anaerobic decomposition in the composting process, it's occur a lot. We get some example of common VOCs in municipal waste. So this is very general. The methane, which is odorless, and butyric acid, propionic acid, aldehydes, and terpene. But if we go in the different areas I mentioned before, for example, reception building. Sorry, the tables and graphics are in Spanish. In the reception building and storage pit at the end, we see that we have curves between 13 and 11 ppm in curves, which in orders we are about 6 to 2.2 thousand odors units. And if we look at the main groups of curves we got in this part, it's aromatic hydrocarbons, ketones. After we got some terpenes, some alcohol a little bit, and aliphatic hydrocarbons, organic acids, esters, and some halogenated compounds. Okay, and we see for example, during 48 hours, we can see when we have some peaks due to a very high quantity of trucks coming in this area. If we go to the pretreatment building, so here we can see that we got the curves quite high, between 31 or 4, nearly 5 ppm, depending on the hour in the day. It means depending on the how it's working, and between 12.3 thousand to 900 odor units per cubic meter. And the main families are the same as the one we got in a reception area. Okay. If we go to specific equipment in pretreatment, so it's quite different. If we go to a ballistic separator, for example, we are about 22 ppm of COV, but in odor it's only 3.5 thousand odor unit. In a refuse press, the quantities are lower in terms of VOCs, between 3 to 10 ppm, and 400 to 2,000 odor units, depending on the moment in the day. Okay, and in terms of family, it's the same. We got the same main families, but we start to have in some equipment aldehydes that we get in the top of the columns of each equipment. If we go to a composting unit, so here we are in a composting building. So we got VOCs around 17 to 7, depending on the moment of the day, and between 6 to 3,000 odor units. And it occurs the same in terms of the families of VOCs. We are with the same families, with some aldehydes at the end, esters and aldehydes in the composition of the VOCs. So as somebody before speak about the limits, we have to comply with some limits in terms of emission, the total VOC. So it's indicated in the decision of the EU in the 2018/1147. Okay, so the BAT. And if we go, there is a definition of VOC based on an article of the directive 2010/75, and in the BAT 34, it explains the different technologies to reduce the emission dust, organic compounds and odorous compounds, including H2S and NH3. And in this same BAT, there is some associated emission level. that have been mentioned before at the beginning of the webinar. For the total VOC, between 5 and 40 milligram per normal cubic meter. Obviously, 5, it must be with a TO, that's clear. But the value of 40, it's normally the limit that is asked to comply. And when we go to the way to make the measurement, the control of this parameter, it's indicated in the BAT 8. It's the directive 12.6.19, which indicates that when this is the Spanish version, but we have to use a flame ionization. And what happened at the end, we are speaking about odors, because as we see, one of the limitation is total VOC and odor concentration. We are speaking about odors. We have the dust, H2S and H3. Well, there is no limit for H2S, but NH3 in the BAT. But we are making the measurement of total VOC with flame ionization. So it means that the methane, which is odorless, will be included in the measurement of total VOC. And as I said, in the reception area, the storage pits, or in the composting phase, and obviously in anaerobic digestion building, when we get dehydration of the digestate, the output material of a digester, at the end there is some methane, and it means that when we get the limitation only on total VOC, it includes the methane. So actually, there is some facilities where it's quite hard to comply with some values when they are not asking for 40 milligrams per cubic meter, but for 30 milligrams, and the value of methane is making that it's quite hard to comply with the limits they are asking when they are asking for a very low limit. If you have a biological treatment, or well, if you don't have a thermal oxidation.
1 minute, Mark.
Okay, in some countries they are starting to speak about non-methanic VOC to avoid to have methane, but there is not a measurement procedure existing. The major cost of managing the other problem in the facility is energy consumption. This is the challenge. So how to ensure acceptable condition in a municipal waste treatment building, increasing the air change per hour. It's a lot of money because it's a lot of flow. So this is not an issue. In the past, the grid of aspiration of piping was more like you can see in this picture of a drawing, but it's a lot of pressure drops. In this picture, it's nearly pink, but you can see this type of concept of ventilation. Also, some aspiration point in some equipments, but it's a lot of pressure drops. So we have to think that we got some ways the process, the equipment. There is natural convection, and we have the air with the odorous compounds. That is there is a convection to the upper part of the building. So with the normal louvers of normal concept, usual concept, at the end we have stagnant air, which creates some problems, because with humidity you can have rain effect in the buildings that can eventually create corrosion in the wall and roof building, and we can see it in this upper part over there above pulper in a facility. So this is an important issue. Okay. That shows that in Urbaser, one of our main objectives is decarbonization, and we're doing this. One of the ways is to reduce electrical consumption in all the ventilation systems. So what I explained, we have the waste composting and the stagnant air, because the extraction can't have an impact on more than some, let's say 1 meter in the best case. So what our concept is to create a dynamic zone using transfer fans to push the air near the grid and near the extraction pipe to reduce the quantity of piping, the length of the piping, and the pressure drops. Okay, so because those fans are only 0.3 kilowatt each fan, and there has an air supply range of about 20 to 30 meters, so they can push the air and transfer the air, contaminated air, near the grid. So this is the concept we developed with a company. Okay, and to check this, we carried out a fluid dynamic CFD study. Okay, to check the design. We mainly focus on temperature, velocity, and LMA. The local mean age, it means the air age, the time required to supply air to reach a point in space from a supply inlet. Okay, so for example, we have on the left the actual state, the old state, let's say, and with the new design, the change in temperature. So we were able to reduce 5 and more than 5 degrees the temperature in the building. In that case, it's at 0.5 meter high, and at 6 meter we got the same impact. So the conditions are better in terms of temperature. We move the air, and in terms of LMA, age of the air, we can reduce more than 50% the retention time, and to avoid stagnant air and some problems you can have in some buildings. Okay, and well, circular economy challenges and R&D. So we got new developments in environmental technologies at the Alfonso Mayo Basser Technological Innovation Center, and we work a lot in all the ventilation and air treatment issues. And you get my emails if you have some additional questions.
Thank you, Mark. We are a little late.
Yeah.
The last speaker, oh, sorry.
I do my best, but
Please extend your explanation. The last speaker of the second session is David Cartelle. He's Director of Operations in Spain for Suez Air and Climate Business Line. He has over 25 years experience in ambient air quality management, including as Director, co-founder of Troposfera, now part of Suez Spain. With the International Suez team, he's a member of the Air Solutions Scientific Committee and the key expert on air quality for the Suez Group. Hello, David.
Thank you. Hello. Can you hear me?
Yes.
Yes, perfect.
Perfect.
So I'm going to share my screen. Okay. Can you see my screen?
Yes, but
Yes.
not in the mode of presentation.
Yeah. Let me put in. Okay. I think now you can see in full
Now,
screen.
yes.
Okay, perfect. So good morning to everyone. I would like to thank to the organization and all the people who is attending this meeting today for participating in this interesting webinar, and also congratulate the speakers for the high level of their presentations. Okay, so I'm going to talk about new tools for the management of environmental odor pollution, where I will try to explain our advanced air quality and other data management tool, focusing in a successful case, which is the MITLOP project at the Emasesa composting plant in Sevilla. Okay. So, well, firstly, just a brief introduction to who we are, Suez. Suez Group is a French company dedicated to waste management and water cycle. With an international presence, and in Spain, we have local offices in Galicia, in Alicante, Madrid, Barcelona, and Bilbao. So within the company's structure, a small part is made up of the air and climate business unit, with around 100 professionals to support the industry and also public institutions to improve the air quality, provide innovative technology-based solutions in, let's say, the fight against pollution and climate change. So globally, in the air quality and climate business line, our main offices are located in Spain with more than 30 employees. In France, as you can see here, in Italy and UK, and also in Middle East, and also we have local partners throughout the world. Okay. The portfolio of services we offer cover different parts dedicated to the environmental diagnosis, monitoring of pollutants, and for sure odorants, and finally the treatment of gases. So and all these portfolios is through the different air advance and climate advanced solutions, which is the name of our services. So maybe one of the most powerful technological solutions is the Advanced Vision 360 platform, where we integrate data from monitoring stations, monitoring systems and forecasting systems for sure, all with the aim of offering a complete, let's say, a complete solution that includes historical data management to understand the past, early warning systems to manage the present, and forecasting systems to prevent future damages. Okay. So in that case, for the mid-lob project, we have deployed the Advanced Vision 360 solution, the platform. Just to say that mid-lob is an eco-innovative model for bio-waste management in the Seville metropolitan area. And well, this solution has been developed through the mainly three innovation projects, one of which is the deployment of these, of the smart platform for monitoring air quality and others in the Complejo Ambiental de Copero. The main objectives of this project, maybe the objective is was on the one hand to deploy a network of air quality sensors around the composting plant as an early warning system, consisting of H2S ammonia plus VOC detectors. Okay, and on the other hand, the service consists in the deployment of equipment with electrochemical sensors in emission, in one of the outlets of the biofilter of the composting plant, and provided for sure with a sample conditioning system in order to measure the emissions. And at the same time, the platform also had to collect data from four other emission measurement devices, as well as other sensors in plants such as ammonia detectors, which are located inside the composting buildings. So the Air Advanced platform was deployed here, and it's important to note here that maybe one of its main features are the ability to customize and fit to the customer needs in that case, and the fact that it is an agnostic platform. So that means that we can connect every kind of sensors to our platform. It has a modular structure, as you can see here, which we will see in the next slides. Okay. Okay, so the first module is the supervision. I mean, has a dashboard with a system of colored cars according to the air quality index or odor index or emission limit values. So, well, these colors and thresholds are fully configurable by the user. And on the right, you can see there is a map showing the different sensors with the location and the color associated with the corresponding index. Okay. The sensors are grouped in different in networks, and that means that it is possible to differentiate between, for example, the early warning system, the emissions equipment, or the sensors inside the composting plant. Okay. Okay, so by clicking here on any of the networks, the different associated sensors are displayed, where we can see the latest data of the different parameters that we are measuring. Okay. In addition, we can see in a more detail, as you can see here, the last 24 or 48 hours by means of interactive tables or graphs, where we can choose the different parameters we want to visualize. So the next module, which is the supervision module, for the analysis of the historical data, is, as I mentioned before, is dedicated to the analysis of historical data, where we can choose for sure the dates, seasons, or different types of different kinds of representations. Okay, it is based on the OpenAir software, and here, for example, we can see a pollution calendar, which is very useful to know which days we have detected higher levels of pollutants or odorants in that case. And here is another graph, another example of graph showing the evolution of concentrations. Okay, so in this sense, the tool allows for different types of data aggregation as well. I mean, you can choose between minutal or hourly or daily averages. Okay. Another example is the representation of a polar plot on the map of the area. In that case, representing the location of the sensor, which makes it possible to know from the concentrations that we are obtaining in the different sensors and the wind speed and direction data, which is the most probable origin of the concentrations of the different pollutants. Okay, this is another kind of representation of the data. An important part of the system is always the data validation, because we always need to validate the data in order to segregate the data. I mean, the invalid data for the valid one. So by means of the validation module, invalid data, is flagged via a flag, which is a letter. So that means that the raw data, let's say the original data, is always stored in our system. Okay. The other part of supervision module is the module for on-demand reporting. So here we can create automatic reports for different periods and taking into account the existing regulation, let's say, exists. A report, I mean, we can create following this form a report with graphs and data tables with the statistics. It's generated automatically, and also automatically stored in the system folders and can be retrieved anytime whenever you want. Just to mention here that the system is also prepared to work with NASAP, the citizen science website that collects other nuisance data, and that currently, through an agreement between Suez and NASAP, Air Advance integrates its services. Okay. The last part of the platform is related to the models. So this module is called Hypervision, and as I mentioned before, is dedicated to the management of data from models. So on the one hand, it has a back trajectory module, which is this slide that you can see now, and this module has these back trajectories at a very high resolution in order to calculate the probable origin of a pollution or other impact by using mathematical models. So the system is fully interactive. So it's
sorry, David, 1 minute.
Okay, perfect. So going to the forecast, another module we have is related with the forecasting, and here we can see the model. I mean, the results of the model chain for WRF, CalMet, CalPAF in that case, with a time horizon of 24 hours. The modeling system is fed with emission data from the biofilter, as well as data from other concentration obtained by our measurement campaigns. Okay. And finally, what we have is a module for on-demand model run. So in this way, the user can run his own modeling, introducing new sources or changing the emission rates of existing sources, blah blah. So we have obtained our own results without any knowledge about models. Okay. This is just an example about one simulation doing by the user for a new source, for example. And in addition, the tool has a visualization system that allows us to compare different, let's say, scenarios, different situations. So acting as a digital twin. And finally, this is the end, I promise. Air Advance sends a daily forecast report by email with a risk calendar. This calendar is strictly based on meteorological conditions, such as the existence of thermic inversions and wind direction, blah, blah. So that means that we can, well, advise or avoid to the user about the, I mean, maybe any complex situation. Just to say that in that case, that the as an innovative component, as is in experimental phase, the system has been developed to calculate odor concentration from the concentrations obtained by the air quality and emission sensors. And these calculations are based on the Weber-Fechner law, in which the odor concentration is initially calculated on the results of H2S mainly and ammonia. Okay. To finish, just to say that we are developing our own continuum emission system. I mean, for measurements, mainly for H2S, ammonia, and VOC, and try to couple electronic noise. Well, but based on a conditioning sampling, a new conditional sampling, in order to have the less losses in the system. Okay, so that's all. Thank you very much for your attention, and if you have any doubt, don't hesitate to write me to my email or even contact me by phone. Thank you.
Thank you, David. Let's jump right into our next session. We focus on bringing the change in waste management from challenge to solution. The first speaker is Laura Mejido, PhD, is a researcher at Cogersa with background in chemical and environmental engineering. She has contributed to over 30 R&D projects, including EU-funded initiatives like Plastics. Is a project of the program Horizon Europe, Life in Fusion, and S-ONA for Life. I don't know the real name. I think it's S-ONA for Life or SON for Life program. Her work includes 23 scientific publications for patents and international research experience across Europe. Hello, Laura.
Good morning. Can you hear me?
You?
Can you hear me?
Yes,
okay.
We can.
Okay. Thanks. Can you see my screen?
Yes.
Okay, so I'll start. Thank you for inviting me to join you today. As Gloria mentioned, I am Laura Mejido. I'm a researcher at Cogersa, which is a public waste management company located in Asturias, in the north of Spain. And I'm going to present the LIFE project, Z-ONA for Life, and how we aim to transform a hazardous industrial waste into a valuable resource, promoting circular economy. To give you some context, the project is titled Aluminum Foundries Circularity by a holistic zeolite production for effluent depuration. And it's abbreviated as Z-ONA for Life. The letter Z stands for zeolites, and the letters O and A, read as ONA, means good in Basque. So the name might translate as zeolite good for life. The project began in September 2023 and will run for 4 years, ending in 2027. It is co-founded by the European LIFE Programme for the Environment and Climate Action under the Circular Economy and Quality of Life sub-program. Our main objective is to demonstrate at pilot scale that salt slag, a hazardous industrial waste, can be transformed into a synthetic zeolite. And we aim to prove that this process is both technically and economically feasible. This zeolite will then be used for gas absorption, for example, flue gas treatment in the aluminum sector, and also wastewater purification. For those less familiar with the aluminum sector and its challenges, here's some background. Aluminum is a lightweight metal with excellent properties: elasticity, thermal and electrical conductivity, corrosion resistance, and low melting point. And it is widely used in construction, aerospace, defense, packaging, medical, and other sectors, making it critical for many industries. Global demand for aluminum is projected to grow by 50% by 2050, reaching over 107 million tons. For this reason, it is considered a critical raw material in the European Union. Circularity in the aluminum sector has advanced significantly, particularly through secondary metallurgy, where scrap aluminum is recycled. Indeed, in Europe, 30% of aluminum supply comes from recycling, which reduces energy consumption by 95% compared to primary production. However, a key challenge remains, which is the waste generation during this recycling process, particularly salt slag. Indeed, about 0.5 tons of salt slag are generated per each ton of aluminum that is produced, with an estimated 26 million tons expected globally by 2027. This salt slag is classified as a hazardous waste in the European Union due to its flammable, irritant, and leachable properties. In fact, both its large quantity and its hazardous nature present serious management challenges worldwide. Given this context, Zetaona for Life focuses on several aspects, several objectives. Improving circularity in the aluminum sector by valorizing salt slag, bridging the gap between lab scale and industrial scale valorization, developing a new zero waste process through byproduct recovery, demonstrating the use of Zetaona zeolites for effluent treatment, exploring the commercial potential of Zetaona zeolites, and finally, assessing how project results can influence European policy, legislation, and industrial practices. So why transform salt slag into zeolites? Well, zeolites are essential inorganic materials in the chemical industry due to their porous structure and also ion exchange properties, which make them highly effective in various applications. So in 2021, the global zeolite market was valued around $12 billion and is projected to reach $14 billion by 2026. That is a growing rate of 3% annually. So the synthetic zeolite market reached $5.9 billion in 2023, driven mainly by the demand from detergent and adsorbent manufacturers. So, given this data and its relevance, we need to know more about this salt slag. Well, this salt slag is rich in aluminum oxide with around 40 to 50% in content, which makes it a promising raw material for this zeolite production. And to achieve the required composition, we need to combine it with other industrial waste rich in silicon, so that we can also create industrial symbiosis between two sectors, aligning with European priorities. In a nutshell, Zetaona aims to close the loop between waste generation, treatment, and reuse by converting hazardous waste into value-added materials like zeolites and integrating them into real-world application. And this is made possible by a multidisciplinary consortium of partners. CSIC, with scientific expertise in zeolite synthesis and pollutant removal. Alusigma, a secondary aluminum producer directly involved in circularity. Inderen, with expertise in engineering design and installation of pilot plants. Ferrosadin, with experience in metallurgical waste recovery. Compla, focused on software and digital communication. Trusted, expert in market analysis and communication strategies. And finally, Cogesa, the company I work for, which is, as I mentioned before, a public company focused on waste management. Some data about Cogesa. Cogesa is a public company but belongs to a consortium. It's a public waste management consortium in Asturias, which is constituted by the regional government of Asturias and all the municipalities, the 78 municipalities. And for instance, in 2024, we managed over 872,000 tons of waste, of which 47% was municipal waste, but 15% was industrial waste. And this is possible because we have an integrated center of around 4 square kilometers inside. And here we have many types of facilities in which we can manage all types of waste, except radioactive and explosive. We have several treatment plants, 3 landfills, non-hazardous for non-hazardous waste, for hazardous waste, and for inner waste. And also an R&D area that we call the Open Lab. In this Open Lab area, which you are seeing a photograph in the slide, we will host a pilot plant. It's a pilot absorption treatment unit in which we will test these theta-ona zeolites for wastewater purification. And the target is the leachate that is generated in the non-hazardous landfill. But also we can treat other kind of wastewater that we have inside our wastewater center. We are currently testing theta-ona zeolites for treating ultrafiltration permeates from another LIFE project. What you see in the photograph is a pilot plant from the project LIFE Infusion. And these permeates are produced after being stripped and being ultrafiltrated in different equipment that they have in the pilot plants. But also, we want to test theta-ona zeolites for purification of gas streams. For example, at Alusigma's aluminum ingot plant, we can control the composition of these gases before being released into the atmosphere. Although odor control was not part of theta-ona original focus, we've seen that is growing interest, scientific interest in using zeolites for this purpose, including synthetic ones. So if there is potential for collaboration in this direction, we'd definitely be happy to keep in touch with the Abate team or others that will be interested. And we want to obtain our objectives in the project because achieving the goals of theta-ona means contributing to different European strategies, such as Circular Economy Action Plan, the European Industrial Strategy, the Waste Framework Directive, the Sustainable Development Goals, and the European Green Deal. So a key environmental strategy is to transform waste into valuable materials for industrial reuse, supporting sustainability and innovation. I hope this fast overview has given you a clear understanding of goals and the significance of the theta-ona project. And I warmly invite you to join us on June 19th, when we will be hosting a hybrid event as part also of the Green Week. And you can find more information and register using the link that is showing now on the slide. And thank you for your attention.
Thank you, Laura. Now we will go to the next speaker. Is Agustín Gutiérrez. Is an associate professor at the University of Barcelona with 25 years of experience in the field of chemical sensing. He has led 7 research projects as principal investigator and is currently the coordinator of the European project SNP-DRONE. Agustín explain us this European project, the SNP-DRONE. Okay.
Hello, thank you. Thank you, Gloria.
Hello, Agustín.
Hi. Let me share the slides with you. It'll be just a second. So, sorry, I'm just trying to share the correct one. Which should be this one here. Well, I'm sorry, I'm gonna try to do it differently because it's not.
If you want,
okay.
You could continue with the next speaker, and I can put your presentation in the screen, but I need to go inside my Word screen. That is not easy.
Yeah, sorry. Yeah, I don't know why it's not showing up. Because I have it right here, but it's not showing me the screen. Let me just one more try.
No, we're waiting.
Before we move to the following one. So for some reason, it doesn't show up the correct one, which is the LIFE ABATE. Sorry about this. So let me do it again. Very sorry about the delay. Okay. Okay, here we go. Let's see if this works now. So the problem is that it's not showing me the actual presentation on when I try to share it, which I don't know why. Because I just closed all the rest.
Don't worry, Agustín.
So yeah, sorry, I cannot find it.
Continue with
Gloria, if not, you can send, if you have the presentation in your email, you can send it to me and I will share the presentation through my screen. I mean,
Do you have the PPT?
Gloria, do you
version?
have
Yes,
it?
yes, yes, you have, but in the word screen, inside the.
But you, Gloria, you have it in your email, no? I guess.
Yes.
Send it to me and I will share it. Maybe it's easier. I don't know.
Yeah, probably. Sorry about this. Let's see.
No, but
Because
I can
it's not
share my
showing up.
screen. I can share my screen.
You
No
have it?
problem.
Okay, good.
Yes,
Thanks.
I have it.
Sorry about this. I don't know why it's not showing within the list of all the presentations that I have here, which is supposed to be because it's open right now. So I don't know.
But I have the PDF.
Okay, let's go with this. Yeah, I mean, sorry about this.
Do you can see it now, my
Yes.
screen? Okay.
I can see it now. Yeah, let's go with the PDF. There is a video, but I mean, we will skip this. I will just explain it. That's fine. Yeah. Please, can you presentation mode or that should be
No,
fine,
it's
right?
the PDF.
Okay. Yeah, but if you do Control L, maybe it goes to full screen or not. Well, whatever it is. Okay, so I will go with it. Sorry about this, all this mess. Yeah, well, but so thank you, Gloria, for the presentation. So I'm Agustin Gutierrez, professor at the University of Barcelona. I'm coordinator of the Snifferton project, which is what I'm gonna tell you about. So I want to tell you what we have done during this project, these 3 years already of project, the objectives that we have, and the results that we already have. So in this slide, you can see that this Snifferton project is a European project that belongs to the Attract call, which is a call, a special call, which is multidisciplinary, thought to bring instruments to a technological high level, so to be commercialized afterwards. And it is a cascade mode funding in the sense that they have a big project in which they assign six projects between them. We are one of them. They are quite big. They are 2 million euros project, and it's composed of 6 partners. So we are 2 universities, University of Barcelona, University of Lancaster. We have 2 companies, DAM, which is, well, unfortunately, well, if you go back, Gloria, to the, here, DAM, which is, sorry, thank you. DAM, which is unfortunately not active any longer. GSS also, which is a company in Scotland that do sensor fabrication, chemical sensor fabrication, and 2 research institutes, IBEC and SINTEF. So the main idea of the project is to build and demonstrate a drone-based system to monitor volatile chemicals and others emitted by wastewater treatment plants. So yeah, now if you can just go to the following slide. Thank you. So the main idea of the project is, well, use a drone as a mobile platform with an IOMS, with an instrumental odor monitoring system mounted on the drone to monitor chemical sensors, to monitor volatile chemicals and also odors. We wanted to test this in initially three wastewater treatment plants. So finally it was 3, but considering that Pinedo is 2 in 1, so probably we can say that we have tested in 4, plus 1 composting plant. So the novelty of the project is, well, the drone operation, of course. So being able to have this mobile platform that moves around the plant and having real-time measurements. Also, that we're able to calibrate in-flight conditions with transient signals. So basically, the signals that we have on the drone on real time is what we use to calibrate our models to estimate the odor. And also, I was a little bit ahead of myself here, the development of algorithm to predict human odor evaluation. So basically, from the odor readings, have a model that from the sensor readings is able to predict the odor perception. And of course, the drone brings us the possibility of do a regular and fast measurements on any plant that we want to do. Okay, good. So now we go to the following slide, which is the specific objectives that we had initially on our project, which are first, we wanted to develop a high-performance multi-gas end-year sensing unit. So basically, we wanted to have a optical-based chemical sensor that was light enough, fast enough, and that the consumption was low enough to be mounted on a drone, something that with commercial units was not able up until now. The second objective was to bring this unit to a matureness a level of technology to be able to be commercialized. The third was, with these two elements, we wanted to have mappings of wastewater treatment plants emissions. So basically have readings of the chemical volatiles. And along with that, we have goal 4, which was not only the chemical volatiles, but also the others, is something that we wanted to monitor. So have also a map of others of these wastewater treatment plants. We wanted to show also the flexibility of the platform, this platform, to not limit it ourselves to wastewater treatment plants. And we also, at the end of the project, we tested in a composting plant. And finally, well, the final goal, along with the goals of the call, was to bring all this system to a mature, technological mature level. Okay, next slide. So the overall outcome, as I said, this project started in 2022, so it's been 3 years already, and it's finishing actually at the end of this month. So, and we already have the results of the project, and the overall outcome is what you can see here. So in the center part, you can see our drone-based odor monitoring system, in which we have our drone with the, I cannot point, but if the elements that are mounted on the drone are the near IR unit, which is on the right of the drone picture. And also at the bottom, we can see an IOMS, yeah, right here, IOMS along with a sampler, with an air sampler, because we not only need to measure to have the sensors mounted on the drone, which is what we have here, but also a sampler that allows us to collect air samples in order to bring them to a human panel afterwards. And the base station that is just to control everything all together. And so with this system, we were able to do 3D maps of environmental pollution, 3D maps of environmental odor on the certain wastewater treatment plants. And also we developed an application, which is this map of Spain that you have here on the right at the bottom, where, well, I mean, here, this was a video, so we cannot see that here in the PDF, but the idea is that you can click on each one of these locations, which are the locations of the wastewater treatment plants that we have measured. And then you go to a more detailed map of the plant where you can see the emissions. So you can see the specific measurements that we have done, a map of the emissions, and also a map of the others. Okay, we can go to the next slide. Thank you. So we, of course, before we go to measure in plants, what we did was a characterization of our instrument. We did several characterization tests. So to characterize the IR sensing unit, basically what we did was lab experiments in controlled conditions of temperature, relative humidity, where we were exposing methane and ammonia to our sensor, which is the two gases that is able to sense. And what we can see here, top left part of these figures here, that they were exposed to 25 and 50 ppms of methane, and we can see that they have a nice response. So we can say that we have a resolution on the order of ppms on methane. And also we expose also ammonia, 200 ppm of ammonia, in which we have a response as well. So if we look at the bottom now, one thing that we wanted to obtain with this system is being able to have, to some extent, a good resolution of the mapping of the plumes that we can see in any plant. So to do that, we have to have a fast response. So we have to have a good temporal resolution. We have to have also a good spatial resolution. So for the temporal resolution, it was very important for the sensors to respond fast. And to test this, what we did is to build these wind tunnels that we see, this wind tunnel that we see at the bottom right, where we just have a fan that is creating a plume, and on the other end of the tunnel we have our sensors, and we can see that this allowed us to check response of our system on the order of seconds. So we have a temporal resolution on the order of seconds. And finally, before we went to the plan, of course, we wanted to test the entire system together. So we had to do flights, and to do flights in a safe way, what we did was to use the drone lab that is in Castelldefels, which is a closed area in which you can just fly your drone without any limitation, and where you can test for hours your system. We can move to the next slide now, Gloria. Thank you. So during these 3 years of project, we have tested our system in all these plants that you can see here. So we have 4, considering that Pinedo is 2, 4 wastewater treatment plants, 1 composting plant, and actually next week we are going to measure in Friselva, Girona, which is a pork meat industry. So on total, we have done 18 measuring campaigns, which are 2 days per campaign. Our campaigns consist in flying our drone or going with our instrument by foot, doing measurements with the chemical sensors, but at the same time taking air samples and bringing these air samples to do olfactometries. And we ended up with a total of 128 olfactometries at the end of the project, which is quite a good number. Yeah, I think we can move to the next. Yeah. So the final results that we obtained, and we wanted to highlight this, because it was one of the important aspects that we were targeting, was first the fast response of the chemical sensor array unit, which is mostly based on the small size of the sensor chambers that we were able to build, which is something that you can see on the top left part of the figures. So these chambers is what you have there. So we were able to reduce a lot, and they allow us to have a sensor response which is of around 3 seconds, which give us a good temporal resolution. We have also a high specific multi-gas and direct sensor unit for ammonia and methane, with low weight and low power consumption, which is what you can see exactly here in the figure at the bottom, where you can see that is very specific. Here is presented with ammonia and methane, and also with 3 other compounds, and it only responds to these 2. And on the right-hand part of the figures, we can see a concentration map of wastewater treatment plant. In this case, a concentration map of Molina de Segura in Murcia, where we can see that we have this color-coded intensity of the odor. And at the bottom, we can see, well, sorry, this is concentration. The upper part is concentration. At the bottom, we can see the odor map in the wastewater treatment plant of Torredembarra. Okay, so we go to the next one. Yeah, so in the final slides, what I wanted to do is to highlight one of the, I would say, important parts of this of a project like this, which is the calibration model between the IOMS, the instrumental odor monitoring system, the chemical sensors, and the odor. So basically, the idea is that we built a model for each plant that we go. So we have a model that is able to predict from the sensor responses the odor that the human panel is predicting. When I say odor, we are limiting to odor concentration, which is what we are studying here. So we have a model that transforms sensor responses to odor concentration. And an interesting aspect is to see if this model is maintained across plants, because that will be very helpful in the sense that you can just test it with one plant and then use it for the rest. And what we can observe is that something that doesn't happen in general. So we can see here 3 models on 3 different wastewater treatment plants, Molina de Segura, Torredembarra, and Pinedo, where the models are slightly different. And not only this, but the sensors that they use to do this prediction are also, they're chosen to be different. So in general, what we can see is that this model is something that is not maintained. Furthermore, and if we go to the following slide, if we try to use a model that we obtained from, in this case, from one of the plants, in this case of the plant of Torredembarra, if we try to use this data, so data of Torredembarra, so training our model on Torredembarra and use it in another wastewater treatment plant, in this case, Molina de Segura, what we can see is that the errors that we obtain increase tremendously. So we can see the bias here, if you can look at the table. So the bias goes from 1 to 6.88, the standard deviation doesn't move that much, but the error, the root mean square error goes from 2 to 8, and the correlation lowers from 0.8 to 0.66. This shows us that a direct application of the calibration of one plant to another doesn't work. So next slide, thank you. Yeah, and the good thing about this project is that now we have all this data that we can leverage in order to find a way of transforming one model, the model of one plant, to another plant, which is something that we're working with. We don't have final results yet, but it's something that is very interesting in order to reduce all the cost of calibration and recalibration. So one thing that we had to do is to observe with this data the difference across wastewater treatment plants, and that's something that we can see here on the distribution of olfactometries. So on the first plot, top left, we can see the distribution of olfactometries for the 4 different plants. And also we have a PCA where we can see the other concentrations where they don't cluster together, meaning that they cannot the distribution is different, okay? And also what we can see on the right-hand side figure is the models that we have used, that we can see that they are different as well. It's a representation of the model. So each color represents a different model of a different wastewater treatment plant. So if we go to the following slide, which is the last one. So the idea here is that what it would be important is to try find a way to do calibration transfer. So we want to transfer the calibration that we do in one of the plants to the other plants. But this is just one of the scenarios for calibration transfer. And a different scenario also is, and that's something that also requires recalibration, is the 3 scenarios that we have here. So the first one is the system drift. So whenever you calibrate on a certain plant, and certain time goes by, let's say 1 month, 2 months, your sensors have changed due to drift or other reasons, and you want to use the old model in order to analyze your data. But to do that, you have to do certain transfer calibration. So the second scenario will be what I mentioned. So the different plants. So you calibrate in a primary plant A, and you want to use that to a primary plant B. We have seen that we cannot do that directly. So we have to do certain transfer from one model to the other. And the third scenario is the scaling, in which that also happens to some extent when you calibrate for a certain instrument and you try to use it on an instrument that is built nominally exactly in the same way, but we know that chemical sensors do not respond exactly in the same way. So we will be able, we have to adapt this model in order to use it to these different instruments. So finally, just as a conclusion of this final part is that we are working on these calibration transfer models, which will improve and reduce the costs of calibration a lot. Thank you.
Thank you, Agustin. Now, we move right now to the next speaker and the last of this third session. Carlos Sanchis has a background in material science and electrochemical. He joined Envirochem in 2014, a startup company that aims at developing green technologies and sustainable materials, where he's currently the head of innovation. Since then, he took part in seven EU projects related to the production of high-end activated carbons and could bring improvement to a wide variability of industrial applications such as energy storage, hydrogen storage, and volatile organic compounds abatement, among others. His interests are focused on the development of singular nanoporous materials out of bio-waste, the understanding of the absorption mechanisms of key gases and anions, as well as the development of downscale solutions for the regeneration of spent absorbents. And Carlos Sanchis will present us the carbon project.
Thank you very much for your kind introduction, Gloria. Okay, so yeah, I'm Carlos Sanchis from the company Envirochem. This is a small company, a startup located in Navarra. Our history goes all the way back to 10, 12 years ago. And that is exactly the time when we were taking part in this carbon project. This is not like the other two projects that were presented before, which are more recent. This is already 10 years since it concluded, but I think that some of the insights that we got there are still relevant. So I think it's good to come back to them and share with all of you. So this is a deep dive into the VOC abatement with tailor-made activated carbons. This is our business, let's say. We are a company mainly doing tailor-made activated carbons and another, development of other green processes that I will also introduce a little bit later. And our goal entering this project was to be able to establish correlations between a wide list of VOCs of industrial relevance and the properties that we could induce in activated carbons, which are tailor-made, which are made out of local biomass, and that we can control really, really well. So to start with this, the actual title of the carbon project was Innovative Eco-Friendly Activated Carbon Filters for Harmful Vapors and Gases, VOC Purification. So we started by selecting the target VOCs for the study, and we have a representation of hydrocarbons, both saturated and aromatic, wide representation as well of oxygen groups, ketone, alcohols, aldehydes, carboxylic acids, and esters. Also some heteroatoms. So we have halogenated compounds, or at least one halogenated compound, one mercaptan, and also a tertiary amine in the mix. And typical molecular weights were between 60 and 100 grams per mole. So you can also see here the representation of the molecules at more or less the same scale. So you can see that they are all similar in size, but different in their polarity, in their sometimes they have acid groups in some cases. So yeah, that was like the core goal of this project. So the next step for us was to create the catalog of activated carbons that we wanted to test. So initially there was a catalog with around 60 different entries, like 60 different samples. We picked up 4 of them, and all of them were produced by chemical activation. So just as a side note, activated carbons, of course, you probably know or are familiar with that material, but what you might not know is that, let's say, 99.9% of activated carbons that are typically used in the industry are produced not chemically. They are called physical activation. They are produced in Asia, typically out of coal or out of coconut shells. And this is like not really very flexible in terms of properties. It is like the standard 1,000 square meters per gram activated carbon, typically hydrophobic. So you cannot really induce like a lot of properties within that material. And the 0.1%, which is actually chemically activated carbon, is just for one application worldwide. The only one that wants to pay let's say, the additional cost of going for a chemically activated carbon is in the automotive sector, is for the control of evaporative losses of gasoline in the tank of the vehicle. And the reason that they go for this more advanced version of the carbon is because they have constraint in terms of the volume that the carbon can occupy in the vehicle. So if you tailor-made the carbon for that application, you are going to gain absorption capacity. And also in this particular application, they want to gain recovery of the fuel that was absorbed. So yeah, so we use like the same type of activation that the industry uses for producing those more advanced carbons. And we end up selecting those 4. You can kind of see here like a footprint or let's say fingerprint of each type of activated carbon that went into the study. So essentially on the left-hand side, what you can see is the micropore contribution to the pore volume and the mesopore contribution to the pore volume. Mesopores are essentially those pores which are larger than 2 nanometers, micropores below 2 nanometers. So we can induce mesoporosity. That is one thing. You cannot find mesoporosity in typical activated carbon. That is not generated in the other activation process, in the mainstream one. And we can also induce some surface chemistry, like oxygen groups attached to the surface. And in one particular case, we generated one which is not very mesoporous, but it has a lot of polar groups on the surface, also with a wide contribution, the green part here, of acidic groups. Then one which is more rather mesoporous version, but with medium oxygen content, and 2 additional ones which have the lower oxygen content, but they have considerably high mesoporosity. Okay, just to comment very briefly on the technical aspects of the study, we wanted to understand or to check both the kinetics and the equilibrium absorption that we could get. So we defined the kinetic model that we were going to use. This is pseudo-second order. And also we were using a type of isotherm or model of absorption, which is Langmuir-Freundlich. This is, let's say, one of them more flexible because it is compatible with the formation of multi-layers of adsorbed VOCs in this case, and also with having heterogeneous surfaces, which is most likely the case. This is like the typical setup that was used. So the liquid VOC was injected into a flask, which was previously filling with compressed air. The activated carbon was suspended in a basket. The mass uptake in the basket was recorded as a function of time. And after constant mass was achieved, the gas inside the vessel was sampled to check the concentration of the VOC after equilibrium. So we jump now into the results of the project. So first of all, we were assessing, like I mentioned, the kinetics. So let's say that the results that where we found an increase of at least 20% in the kinetic constant is considered a relevant induced property that we are inducing by modifying the probably mostly because of the surface chemistry that we are inducing in the carbon. So we found a number of results. I want to point out that this is like the threshold that we use beyond 20% increase, but in some cases we duplicate or even triple the amount of or the value of the constant. So we can really accelerate or speed up the absorption. So we found a number of results. In this region, you can see those that were actually accelerated. In this one, in this other group, the ones that were decelerated, let's say, like had bad kinetics. So some of the results are easy to explain. For example, polar substances like alcohols attaching quickly to very functionalized carbons, or the same one having bad kinetics at a surface which is not really very hydrophilic because we are not inducing a lot of oxygen groups. But then we have things which are not so easy to explain, like, for example, hydrocarbons having high kinetics on very polar surfaces. So probably this is informing us that the characterization of the carbon is not complete to extract conclusions for certain molecules. But well, just in some cases, I think that it is well informative, and one of them is, for example, this case, the carbon that has some mesoporosity, but not a lot, not a polar surface, and it kind of blocks the bulky molecules, the ones that have heteroatoms with larger atom number. So it has bad kinetics to things which, let's say, would like to absorb better in a mesopore because it's easier to access, and go a little bit worse in a micropore. Now, there are also some molecules, typically those which are more non-polar, let's say, which show little preference or variation or deviation in the kinetics. Now, taking a look at the absorption capacity, which is the equilibrium amount that we can absorb in the carbon. Here, what we see is that except for the more polar molecule, which is the alcohol, where we have high absorption capacity in micromoles per square meter, in the more polar or hydrophilic surfaces, in the rest of the cases, it is this one, the low mesoporosity, low oxygen group content carbon, which is the best one for most cases. It has like top performance in most of the cases. And this is not so surprising. Apparently, we are using molecules that pack together very well inside micropores. So that is probably the origin of this result, because as you can see, this one is the one that has like more micropore contribution. And we completed the study for the rest of the molecules, but just comparing the two carbons the two activated carbons that have like little oxygen contribution, because we don't want to really have a contribution of the oxygen groups. We wanted to focus more on if there was some kind of molecule which favored actually mesoporosity in terms of the absorption, like the wider pores were more efficient for some reason, and that just was not the case. So in all cases, the higher the micropore contribution, the larger the value that we could obtain. There were, of course, also some remarkable absorption capacities beyond 2 micromole per square meter, which indicate that this carbon is very well suited for some of the molecules that we were testing. So we can go now to the main takeaways of the project in terms of the influence of the tailor-made activated carbons. So first of all, chemical activation as a pathway towards engineered activated carbons seems a good idea. It works. The mesopore to micropore ratio, the hydrophobicity, and the pH of the activated carbon surface can indeed influence both the kinetic and the capacity of absorption of almost every single VOC that we tested. But it is also the case that for molecules ranging up to 100 grams per mole in molecular weight, we see that the mesoporosity is not advantageous. So in fact, it decreases like the absorption capacity per square meter. In relation to the kinetics, we observe that all of the variables, the mesoporosity, the hydrophilicity, and acidity, all of them can create acceleration of certain of the absorption of certain VOCs. And the lack of explanation of certain affinities that we found in the study showed that probably we need a deeper understanding and a more, let's say, an advanced physicochemical characterization of the activated carbons to understand what is going on. So I wanted to just present you another project that came after Carboc. It's not like 100% related, but I think it's also relevant. It is only one slide, my last slide. So a couple of years after the end of the Carboc project, we started working on the portable crack project. This is Horizon 2020 project that is also completed by now. And here what we were developing is a solution for the regeneration of the spent activated carbon. Mostly considering water treatment, but also open to gas treatment. And the main goal, of course, here is not the recovery of the VOC, but the recovery of the activated carbon when it is like no longer in service or no longer active. So we found out that there is a problem in the field, especially in the water treatment field, but it is even worse, I would say, in the gas treatment field, because the technology is not cost competitive for a small amount of activated carbon. And we put here a tentative threshold. Under 20 tons, we observed in a survey that many water treatment plants were not accessing a competitive price for the regeneration of activated carbon, because this involves bringing the activated carbon to a thermal regeneration plant, which is typically not in Spain. You have it has to be delivered overseas or to another country, and this involves a big impact in terms of spent activated carbon that cannot be regenerated, and also in the equivalent greenhouse emission due to not reusing the activated carbon. So our solution is a modular solution that is most cost competitive than thermal regeneration, or that the replacement of the spent activated carbon. And it is based on electrochemical regeneration. So this is a modular plant that goes to the site where the activated carbon or the spent activated carbon is produced, and it performs a treatment that allows to recover the indicators like the iodine index or the BET surface area of the activated carbon. Not all the activated carbons, but many of them can be regenerated. And we are still working on this and then on the development of this idea. And in fact, in Horizon Europe, we have spotted already a good topic for us, and which is about replacing heat-driven processes with electrically driven processes. And we think that probably we can check there also the regeneration of gas treatment activated carbons. So that is all from my side. Thank you very much for your attention. And you can find here also my contact email in case you want to learn more or start a collaboration. Thank you very much.
Thank you, Carlos. Thank you to all the speakers, because you have a very interesting and inspired presentations. Now we have time for, we don't have time, but yeah, I think it's very interesting, the questions and answers. Then we move to the chat. We have some questions in the chat. The first question was of Álvaro dos Santos Neto. When you say, this question is for Raquel Lebrero of Universidad de Valladolid. When you say two phases, does that mean that you apply to reactors? If yes, what is the reason? The answer is in the chat, but I think it's good that you explain to all the audience, Raquel.
Yes, sure. Thank you, Gloria. Yeah, thank you, Álvaro, for your question. It's true that I did not have time to go in depth into the in its technology. In this case, the two-phase biotrickling filter is operated as a normal biotrickling filter. So we have a packing material, a packing bed, and we will inoculate the reactor with this enriched inoculum, and the liquid phase will be continuously trickled over the bed. That's the normal operation of a biotrickling filter, and the waste gaseous stream will be fed into the reactor bed. But in this case, what we do is the liquid phase that is recirculating, part of it, depending, well, it can be between 10-20% of the volume. We substitute the aqueous phase or the mineral medium with an organic phase. It's a non-aqueous phase, for example, silicone oil. And what in this way, what we do is to promote or enhance the transfer of the less soluble volatile organic compounds, because as I said, we have a wide range of compounds there, and those that are less soluble in water are more difficult to transfer to the microbial community, to the biofilm for the degradation. So basically what we do is to create this two-phase system. It's just one reactor, the same as normal biotrickling filter, but with these two phases in the liquid recirculation.
Thank you, Raquel.
Yeah.
The next question is of our colleague speaker, Marc Binot. Is there any limits of humidity, relative humidity for the inlet air to the protoconcentrator? And do you eliminate hydrogen sulfate and ammonium before the protoconcentrator? The answer is of our colleague, our partner in the project LIFE ABATE, Calfrisa. Aida Gonzalez said, yes, there is a limit to the inlet air for the protoconcentrator, and managing this is one of the key innovations of the project. In this case, there is no need to eliminate hydrogen sulfate ammonium before the concentrator system. And the limitation of the relative humidity depends on various factors related to process parameters and the specific application sector. If you have a specific case or a study in mind, we will be happy to access it or provide tailored advice. This is the answer of Calfrisa. I don't know if you have any questions more.
Yeah, we can add to this answer, Gloria, that we have taken that into account when selecting the because I probably Aida is here, but she cannot speak.
Yes, I think yes.
So basically, this was a key factor when selected the zeolite matrix of the rotoconcentrator. And yeah, and they try to increase this limit, but of course that will be something that will negatively affect the absorption of the VOCs. So this is very case specific, and we will check if how it goes in the Ecopark 3 in Barcelona, where the humidity of the air is quite high, especially during summer.
As moderator, I have a mandatory question. How do you think artificial intelligence can contribute to developing the odors and volatile organic compounds control? Maybe in the electrical noses or sensors? I don't know. What do you think about it?
Well, I can give my opinion if I may.
Yes, your opinion.
Yeah. Well, definitely in the case of IOMS, instrumental monitoring other systems and electronic noses in particular, it is of great help to use into artificial intelligence, because that's actually what we use to do to build these models between the sensor responses and the other perceptions of the human panels. So that's actually some part of artificial intelligence. There are many types of, different types of artificial intelligence. So we are not talking here about generative AI, which is what is now more popular, but we're talking about machine learning that is also part, and that is able to provide these models. And with the progress that the field is doing, I'm sure the models will improve. But well, mostly more than the algorithms, what we need is data. That's the important part in order to build good models. So that's my take on the question.
More contributions of the speakers about that question or not? You can think about it. The next is, what is the most difficult challenge in the odor treatment? Maybe the lack of legislation in Spain, or what? It's an open question. Or there is some special challenge in technology? I don't know. What do you think that we need to explore more?
So I can give my point of view also here. So definitely there is, in my opinion, there is a clear need of advancing technology, especially I'm talking about what my field of expertise in chemical sensors, because that's something that will help us. Improving this technology will help us to get closer to a monitoring that is easier to, that is more quality and easier to relate with the other perception of the, and also for other reasons as well. But in my opinion, that is one limitation that we have right now.
Thank you. If there is no any questions, we close this webinar. Thank you all for joining us for this engaging and mindful webinar, Breathe the Change, Innovation and Sustainability in Air Treatment at Waste Management Plants. Today we've explored some remarkable examples of how innovation in air treatment can support cleaner and healthy communities while advancing sustainable goals. Our speakers shared their experience, their expertise, and highlighted practical solutions that align with the AO Green Week broader theme of circular solutions for a competitive EU. We've seen how collaboration, technology, and best practices in odors management and air treatment can play a key role in driving the transition towards a circular economy. These insights will no doubt inspire us to continue working together towards a more sustainable future. Because we close, I'd like to extend a heartfelt thank you to our speakers for their valuable contributions and to all of you for your participation. Your engagement is truly essential to move these important conversations forward. Let's keep building on what we've learned today and continue driving innovation and sustainable in our communities. Thank you again for joining us, and we hope to see you at future events. The next event is the next week. Is another webinar of the project Life Infusion. Is related about fertilizers on June 17th, next week. I will send you, all of you, information about the next webinar. Thank you, everybody.
With the support of the European Union's LIFE program.